We called functions of the form f of x equals b to the x exponential functions. And we saw that we needed our base b to be bigger than 0. Let's now look at the graph of these functions for different bases b. We will start with the example b equals 2 that we've been working with. As we have with other graphs, we can start by plotting points, starting with the x value and finding the y value. We have already found several points that we can start with. We saw that 2 to the 1/3 is roughly 1.26, which gives us the point 1/3, 1.26. 2 to the 1/2 is roughly 1.41, which gives us the point 1/2, 1.41. We also saw that 2 to the 2/3 is roughly 1.59, which gives the point 2/3, 1.59. And 2 to the 3/4 is roughly 1.68, giving us the point 3/4, 1.68. We computed this for several points already, up to 2 squared, which is 4, giving us the point 2,4 on our graph. Going a little bit further, 2 to the 3rd is 8, so we have the point 3,8 on our graph. As we can see, as x increases, our function increases steeply. But what if we take x values that are less than or equal to 0? Starting with x equals 0. 2 to the 0 is just 1, so we get the point 0, 1. This is our y-intercept. 2 to the negative 1 means 1 over 2 to the 1, or 1/2, so we get the point negative 1, 1/2. And 2 to the negative 2 is 1 over 2 squared, which is 1 over 4. Giving the point negative 2, 1/4. Continuing this to negative 3, we get that 2 to the negative 3 is 1 over 2 to the 3rd, which is 1 over 8. So we have the point negative 3, 1/8. Notice that if x equals negative n is a large negative number, then 2 to the negative n is 1 over 2 to the n by definition. This is going to be a positive number. It will be bigger than 0, but as n gets bigger and bigger and bigger, our denominator gets bigger and bigger and bigger, which means the fraction as a whole, 1 divided by 2 to the n, decreases very close to 0. If we fill in our graph with more and more points, eventually we get a good picture of what the graph of y equals 2 to the x looks like. Now that we have found the graph of y equals 2 to the x, what does the graph of y equals b to the x look like for other bases? If we plot points, we will see that their graphs are similar. One difference we can see is that since 3 to the x is going to be bigger than 2 to the x, for values of x bigger than 0, the graph of y equals 3 to the x increases more steeply when we move to the right. Similarly, the graph of y equals 3 to the x decreases more steeply moving to the left. Doing this for other bases, we again get similar graphs. The graph of y equals 5 to the x is just going to be even steeper than y equals 3 to the x. At this time, it's worth pointing out that there is a number e, which is roughly 2.72, which we will learn about soon. Y equals e to the x is going to lie between the graphs of y equals 2 to the x and y equals 3 to the x, because 2.72 is between 2 and 3. Now, in all of our examples so far, we have looked at our base b bigger than 1. But the only restriction we have on b is that it's bigger than 0. So what if b is less than 1, but still bigger than 0? Such as b equals 1/2. Well, let's use that b equals 1/2 can be written as 2 to the negative 1. So y equals 1/2 to the x is 2 to the negative 1 to the x. But by our power rule, we can multiply our exponents here to write this as 2 to the negative x. And using graph shifting, the graph of y equals 2 to the negative x is going to be the graph of y equals 2 to the x, but replacing x with negative x will reflect our graph across the y-axis. We can similarly do this for the graph of y equals 1/3 to the x. It will be the graph of y equals 3 to the x reflected across the y-axis. Now let's wrap up what we've seen here. In general, the graph of y equals b to the x is going to be a function that increases at a steeper and steeper rate when b is bigger than 1. And we will get a similar graph reflected across the y-axis if our base b is between 0 and 1. Now we can take this a little further using our graph shifting again. If we have the function y equals a times b to the x, then our graph will be vertically stretched by a. And furthermore, if a is less than 0, then the graph will be reflected across the x-axis as well. In particular, if b is bigger than 1 but a is negative, then we get this graph. And if b is between 0 and 1 and a is negative, then our graph is the one above reflected across the x-axis. Before moving on, I would like to make two observations. First, the y-intercept is when x is 0. So y equals a times b to the 0. But because b to the 0 is just 1, this is a times 1, or a, leading to the y-intercept 0, a. In addition, we can see from the graph that these exponential functions are 1-to-1, which will be helpful when we want to find their inverse later.